Well, thanks very much. It's a pleasure to be here. I'm going to tell you a little bit about research that we've been doing over the past several years at WashU with various collaborators across different areas. And I've titled this talk, Allocating Scarce Societal Resources Based on Predictions of Outcomes. And I want to kind of situate that and talk a little bit about, where does this come from? What are we interested in? And go from there. So more and more, we're living in what we think of as an algorithmically mediated society. So what do I mean when I say that? Well, there's various different aspects of it, but one side of it is that we have more and more interactions between human beings that are mediated by AI, essentially, or algorithms that are sitting in the loop in some way. So, probably all of you have experience with one or the other of these, right? Your interaction with the news, how you learn what's been happening, like where you get your news from, could be governed by who you follow on Twitter. It could be governed by Facebook's decisions as to what to prioritize in your news feed. The kinds of information that you get could be regulated, in fact, by Wikipedia and figuring out sort of what you can learn about a topic over there. It could be YouTube's recommendation algorithm. It could be that you spend a lot of time watching videos in order to figure things out, and you're a big fan of Up Next, and you follow exactly what's happening over there. This raises a lot of interesting questions about how do we study this ecosystem in which human beings and AIs are interacting in this kind of joint society, because the incentives that are created by the existence of these algorithms in the loop are completely different than many of the things that we've seen before. And so that's sort of one aspect of what's going on in algorithmically mediated society. That's not what I'm going to focus on in today's talk, but that's also one of the things that we're thinking a lot about at WashU across disciplines. What I'll be talking about a little bit more today is this area of algorithmic decision making, which is where can we actually affect society? How can we do that in ways that use AI and machine learning to actually help us achieve our societal goals overall? What are the perils and pitfalls of doing stuff like that? And when can we get good results out of that? And I'll be talking specifically about areas where we've worked extensively on designing algorithms that actually participate in these kinds of systems. A lot of these have gotten a lot of attention recently, but algorithmic decision making affects everything that's going on in American society nowadays, right? Who gets a loan? Who gets a credit card? When does the bank decide to cut your credit line? Who gets arrested with predictive policing? What are the kinds of decisions that are made on who gets bail pre-trial and who does not get bail? All of these things are being done more and more by algorithms, raising real questions about what's the balance between efficiency and equity? How do we think about fairness? How do we think about transparency? How do we think about interpretability in all of these kinds of settings? The third thing that I think is really interesting about the confluence of what's been happening is the fact that we now have an enormous amount of data that's available on human behavior. So we have data of digital traces of what people are doing, where they spend their time online. We have all kinds of administrative data sets that tell us things about, ranging from the medical industry, where what kinds of medications have you taken, what kinds of tests have been ordered for you, to interactions with social service systems where we can figure out, okay, what happened if you're homeless, what happened during your intake interview, what did the caseworker identify for you, and so on and so forth. And that's giving us a whole array of new kinds of data and new opportunities to think about how to best use that data in the service of good social decision making. So many of you may have seen one or the other of these books, because this is sort of the counterpoint to the utopian view of it, which says, okay, we can do great things with AI. What are the kinds of things that we should do? I think Cathy O'Neil made a big splash with her book, Weapons of Math Destruction, which talked a lot about sort of the negatives of algorithmic decision making in many different domains. Virginia Eubanks has a really great book called Automating Inequality, which features a number of case studies and a really interesting historical perspective on what she often calls the criminalization of poverty, and how we actually use algorithmic decision making to drive poverty loops and so on. But so these are both books that point out a lot of the perils in these kinds of situations. I'm going to argue that there are many situations in which that these are things that it's very well worth being aware of, and I think that all these books have served a great purpose in raising public awareness of some of the issues that come up, but that doesn't mean that we should throw the baby out with the bathwater. There's really interesting and useful things that we can do with AI in this space of, in particular today I'll be talking about resource allocation in situations where we have scarce resources. So positive side number one, so this is an article, I just took a couple of screenshots. So there's an article on how AI changed organ donation in the US. And this basically talks about how, and this is specifically one of the things I'll be talking about, how the use of AI for designing better matching algorithms has really helped to increase the number of kidneys that we've been able to transplant, and that directly leads to better quality of life, better outcomes for a whole lot of people. And that's going to be the focus of probably the first 2/3 of my talk today. There are other examples, and this is related to the second thing that we're going to do. I think this is just such a cool application, how AI is helping build a better life for refugees, which talks about, these are mostly in Europe that this has been happening, but they've been using matching algorithms to try to figure out where to resettle refugee populations, which is a really interesting problem if you think about it, because different localities may have different preferences over how many refugees they can let in, and so on and so forth. And there are things that are now pretty well known about refugee communities, such as refugees like to go to the same city, for example. It doesn't make sense to break up people coming from many different places and send them off to many different places. You want to try to keep some kind of social structure going. And so how do you solve this? Is a really complex matching and optimization problem, and it's something where AI has really been helping to resettle refugees faster. They've been able to, when they're using these kinds of algorithms, they're able to get employed more quickly, they're able to integrate into society more quickly, all of these kinds of things. So there's all kinds of positive things that are possible as well. So in order to study exactly this intersection of questions, we've actually started a new division at WashU, the Division of Computational and Data Sciences, which is a PhD program for people where our goal is to actually train people at this intersection of questions so that they will come out of this program with expertise in data science, AI, as well as domain depth in a social science, and the idea that they're going to be studying problems that are really at the intersection of AI and society. And so if anyone's interested in coming and doing a PhD or knows anyone who is, please tell them about this program. It's one of the few in the country that are explicitly doing this kind of thing with this kind of goal. So, and if anybody wants to talk about it afterwards, I'm more than happy to. All right. So with all that as sort of introduction, let's talk about the somewhat more specific questions that I want to tell you a little bit about our work on today. And so I'm going to be talking about the allocation of resources, but resources of a particular kind. So the resources that I'm interested in talking about are resources that are in some way controlled or policy regulated by society. So this is different from the traditional kind of resource allocation. So if you think about economics, economics is usually thought of as the study of the allocation of scarce resources. And market mechanisms are known to be very efficient at solving this kind of problem. Why can't we just turn to market mechanisms, right? I have widgets, you have gizmos, we both have money, and we trade so that we both have our optimal bag of widgets and gizmos. In this kind of a situation, everything works out well, under certain kinds of assumptions, but there are many things where we actually cannot use that, right? So we as a society have decided over time that there are things that we want to be able to provide that should not be allocated through market mechanisms. And examples of this include shelter beds and services for homeless households, which I will talk about in the second part of this talk, organs for transplantation that I'm going to be talking about in the first part, but also many other things, right? Spaces in public schools. So if you go to some of the big cities, New York, Boston, Seattle, they often have a pretty complex algorithm for how they end up matching students to different public schools because they have unified public school districts. And again, that's something that you think of as a social good, and you don't want people to be able to use market power or money to be able to make decisions over there. Organs are another example that's pretty classic. Most countries in the world don't want people to be able to use money to trade organs, and therefore it's something that has to be done in a different manner, right? So the question that I'm going to think about is how do we best allocate these resources to those who need them? And in order to actually successfully get anywhere towards answering this question, we have to be able to do a number of different things. We actually have to be able to predict outcomes, right? How good will it be if I allocate this resource to this person? So that's intrinsically a machine learning kind of problem. I want to be able to think about the preferences of the agents, whom I'm allocating these goods to, and what incentives my allocation mechanism creates. And I also really need to define my objectives. What am I trying to achieve through the mechanism that I'm setting up to allocate these resources? And solving these problems is actually a complex interplay of all of these different aspects. So I'm going to start by talking about our work on living donor kidney transplantation. And so this is work that is joint with my former PhD student, Shoshu Lee, who graduated and moved to Google. A number of undergraduates who have worked with us in our REU program over the past few summers, Kelsey Lieberman, William Mackey, and Sophia Carrillo. My colleague, CJ Ho, in computer science, and Jason Wellen, who is the director of kidney transplantation over at Barnes-Jewish. Well, I guess not over at Barnes-Jewish. I'm over at Barnes-Jewish right now, so I'm used to saying that. But so he works very close to where we are right now. And in the second part, I'm going to be talking about homelessness services, and that's work with my current PhD student, Amanda Kuby, and my colleague, Patrick Fowler, who is in the Brown School of Social Work and Public Health at WashU. All right, so kidney transplantation. At any given time in the past few years, there's been 100,000 or more people waiting for kidney transplants in the United States. That is a huge number, and the quality of life of people who are on that waiting list is not very high. They're typically on dialysis. That's a painful, not good kind of state to be in, but you can usually survive for several years on dialysis, so these wait lists are not, they're generally growing because more people are being put on the wait list than are actually getting kidneys at any point in time. In recent years, we've done on the order of 20,000 kidney transplants in the United States. Kidneys are interesting compared to most other organs because we can actually do a number of living donor transplants because we all have 2 kidneys, and if you don't have kidney disease, you're probably going to be okay with just one. And so there's a lot more ability to do living donor transplantation than there is for other organs, for example. Unfortunately, in many cases, somebody may be willing to donate a kidney to someone else, but they may not be medically compatible with them. So this could be because of blood type incompatibilities, it could be because of tissue type incompatibilities, and so on. So one solution that has been proposed about 2 decades ago by a team of economists and transplant surgeons was to do what's called kidney exchange. And the basic idea is very simple. It just says, okay, suppose you have 2 pairs. Over here, we'll just illustrate with a husband and a wife and a pair of brothers who happen to be incompatible with each other medically. But suppose they're actually compatible with the other one, right? So in this case, what we have is husband is compatible with brother, and this brother is compatible with wife. So the solution could be that you do 4 surgeries simultaneously. You take these 2 donor organs, and you transplant them into these 2 recipients, and you do it all at the same time. And then nobody's out a kidney, everybody's getting a kidney, and so you've, without introducing money into the picture, you've actually done what can effectively be modeled as a barter exchange, right? So it's basically, you take one from, you model each pair as an agent, and you say, okay, you take one, you give me one, and then everything is good. And this idea can be generalized, right? It doesn't have to be just pairs. You could think about doing this in long cycles, where you actually have, let's say, 5 different pairs, and you can build a cycle that says, okay, A donates to B, B's donor donates to C, C's donor donates to D, D's donor donates to E, E's donor donates back to A. So you can actually try to find all of these cycles in the graph and try to optimize over this. In general, the state of practice is that what you want to do is you want to try to optimize over pairs and 3 cycles. You typically don't go beyond 3 cycles. But the other thing that's been interesting is the development of chains in this. So every so often somebody comes along and they say, oh, I just want to actually donate a kidney. I don't have anybody I want to donate it to specifically. I just want to do something good for the world. And then they go through psychological evaluations, psychiatric evaluations, health evaluations, and all of this kind of stuff. And if they're deemed sane and in good health, then they're allowed to proceed with this. And that really opens up good avenues to proceed and to do a lot of transplants through one of these chains, because then you're not forced to be matching the originator anymore. Unfortunately, in practice, this hasn't realized its full potential. I mean, it's obviously still doing something, but only about 12–13% of living donor transplants are happening through these kinds of exchange mechanisms. The vast majority of them are still compatible directed donations. And this has partly been because different exchanges are kind of fragmented and we haven't been able to achieve the kinds of gains from scale that we would hope to. But there's also sort of incentive and coordination problems that have been occurring in the market. So there's various solutions that have been proposed. Some of them fall along a couple of different lines. One of these is, okay, can we just make these markets bigger? Can we in some way sort of pool more people, encourage more people to enter the broader pool, and so on? And then the other kinds of solutions that people often propose are medical technology solutions. That is, can we do stuff that is more innovative than things that we've done before? So there's been an increase in the number of actually ABO-incompatible transplants. That's blood type incompatibilities, where they do this long, expensive procedure of actually filtering blood for a while before going ahead with the procedure, which is obviously more medically risky, but allows pairs that were previously thought to be incompatible to proceed with a directed transplant. We're going to think about a different possible solution today. And the different possible solution over here is to say, can we get compatible pairs, that is, a pair where the donor could donate directly to the recipient, to actually participate in the cycle of exchanges in the hope of getting better outcomes overall. So why would somebody do that? And so let me just give you a small sort of cartoon example to illustrate why. Suppose we were able to measure the quality of a transplant. And one sort of crude but perhaps useful measure would be, what is the expected survival time of that graft when you actually do that transplant, right? That is, how long would you expect this kidney to survive when transplanted into this person? So let's assume that that's what these numbers mean over here. So let's look at the case on the left. In this case, if husband, so they are all compatible, but if husband donated to wife, then it would be expected 10 years of survival. Brother to brother, expected 8 years of survival. And that's survival of the organ, not the patient, right? So after that, presumably, they go back on the transplant list, usually. But if we were to do a swap in this case, let's say that the brother would actually get 20 years from the husband's kidney, and wife would get 15 years from the brother's kidney. And obviously, they're both doing better. This is an incentive-compatible kind of situation, and so this is where they would be incentivized to do this. The example on the right is one where that wouldn't happen, even though, as you see in this case, if you sum up the cross transplants, that's giving you a total of 35 years, as opposed to the straight transplants, which are giving you 28. But what you'll notice in this case is that the wife is doing worse, right? And so this violates a basic principle that we want to try to follow, which is that no one should be worse off than they would have been if they'd proceeded with the compatible transplant that we originally had them scheduled for. So interestingly, a couple of years ago, there was a paper published by a team out of Johns Hopkins that attempts to quantify match quality in exactly the way that we care about. So they came up with something that they call the LKDPI, which is the Living Kidney Donor Profile Index, which tries to take various aspects of the patient and of the donor and compute sort of a measure of what would the quality of this be. And you can see that there are things that are specific, for example, donor age and donor sex, but then there's also things that are based on the pairing. So are the donor and recipient ABO incompatible? What is their weight ratio? How many mismatches do they have along different tissue types, and so on and so forth. So you can see that there are actually match-specific properties which give us the hope that actually maybe there could be gains from trade here, basically. So what we did was we first looked at data from, so we wanted to assess, a sort of proof of concept of, is this something that we could actually proceed with doing? So we looked at data from actual transplants that have taken place at a major center, and we did a counterfactual experiment to say, suppose even among the compatible pairs, we were just able to swap counterfactually, like, who was paired with whom, can we do better? And there were a couple of big surprises when we actually did this analysis. So what I'm showing over here is the LKDPI, which is this measure of quality. And for the LKDPI, lower is better, because it's a percentile index, kind of. So lower LKDPI is better. That's the important thing to remember. And an LKDPI of 50 is calibrated to be the average quality of a cadaveric kidney, right? A deceased donor kidney. And the conventional wisdom had always been that any living donor kidney that you're compatible with is better than any deceased donor kidney that you could get, right? And that's the model that the surgeons had always followed. When we actually did this analysis, we were quite surprised, and the surgeons we work with were very surprised, because if you look at the sort of yellowy, orangey bars over here, those indicate how many transplants were done that had LKDPIs around this area, and you can see that actually a substantial number of them had LKDPI greater than 50, which was quite surprising when we looked at the data. Then the other part is, I mean, you don't need to look at both of these, right? One of them is the optimal thing we could have done with all of the patients. The other one is what would happen in practice, which is when you do the 2 and 3 swaps. And what you can see is that it shifts the distribution significantly to the left, right? You have many, many more blue and red much more height on the blue and red bars on the left side of this, which basically shows that we're able to achieve significant gains, hypothetically, by taking this match quality thing into account. So we fit an exponential curve to actually back out from the match quality, the measure of utility or quality that we can try to optimize, because this percentile thing isn't very well defined in additive units, but we can actually think about trying to optimize expected years of graft survival, and that's at least somewhat more meaningful. So we just figured out a functional mapping from the LKDPI scale to expected years of graft survival. And that's just showing you that picture of what that looks like. And now we have to sort of look explicitly at this question a little bit beyond just that proof of concept that we did over there. We have to actually look at this question of how heterogeneous is the match quality? That is, can we actually do a lot better by optimizing in terms of the overall quality by optimizing over the entire population? And so just to do a small picture of what kinds of things we're thinking about here, here's an example where the quality is extremely homogeneous. So in this case, the quality is in fact, so this is simplified, right? We don't have donors and recipients here. We're just thinking about pairs matching. And over here, everything is determined by the value of the blue node. Whoever matches with this blue node will get a value of 3. Whoever matches with this blue node will get a value of 8. And in this case, you can see that it doesn't matter what particular matching I do. As long as I match both of them, the overall social utility is going to be the same. On the other hand, what I've got on the left is a case where I have heterogeneous match values. So in this case, I have that if this red matches with this blue, they get 8. If this red matches with this blue, they get 8. But if I do the straight matches rather than the diagonals, they both get 3s. And you can see in this case, if I go with the straight matches, we get a value of 6. If I go with the cross matches, we get a value of 16, which is obviously much higher. The question that we have to ask is, what does our real data look like? Is it more like what's going on the left over here, or is it more like what's going on the right over there? And so we actually looked at this in terms of the data that we had, and we tried to figure out what is driving the match values that we're seeing. And so what we've got in our original data set is we've got an LKDPI on average of about 37. And what we tried to do was we tried to see, okay, let's look at this last column over here, which is the optimal LKDPI, which is, so if we shuffle the whole data, if we actually figure out what is the optimal set of transplants to make on our original data set, we now get a new mean LKDPI of 22. I can construct various hypotheticals that correspond to different levels of homogeneity or heterogeneity. If everything were completely heterogeneous, then what we'd expect to see is that each of these points is an IID sample from the distribution. And that's the second row over here. And you could see that in that case, I would expect my optimal LKDPI to be more like -2. And that's clearly not happening. So it's clearly not very, very heterogeneous. The next two rows show like what you would expect if the quality were largely driven by the recipient or largely driven by the donor. And you can see again that if it were being driven by the recipient, then we could again still get really good outcomes overall that are much better than what we're seeing in practice. But if we look at it as being largely driven by the donor, then that gets us a lot closer to reality, right? So what this tells us is that actually most of the match quality, not all of it, but most of it is being driven by the quality of the donor's kidney. So there's perhaps a somewhat limited scope to do better, but let's continue with that and see how much better we can do. And we're going to end up doing significantly better than current practice, at least in what we're seeing. So what we did in order to actually move forward with this was to say, okay, so that's a lot of stuff that we've done with the data. In order to figure out what would happen in a counterfactual world, we need a simulator of the arrival process of these donor-recipient pairs that is somewhat faithful to the true data, right? So we built this kind of simulator, and we combined it with a compatibility simulator that's standard in the literature. And then we used that, and as a first step to validate that, we saw, okay, suppose we sample from our simulator, we end up with data that matches our original data set much better, right? We get about 39 as opposed to 37 on the original pairs, and then if they just arrive and proceed with the compatible transplant, and if they don't, and we do all of the swaps, then we get an LKDPI of about 20, which seems pretty consistent. So we are relatively confident that our simulator is doing a good job over here. Now, the next problem that we have to think about in practice, right, is one that has to do with patients. Suppose you come in, so we've talked about the fact that you need to get a higher quality kidney in order to want to proceed with an exchange rather than a donation from your original person who could donate to you if they're compatible. But suppose you come in and you're told, oh, you can proceed with your compatible donor immediately. Immediate is still relative. It usually takes at least 2 or 3 months to go through all the workups and everything that you need in order to be cleared for transplantation, but let's assume that that's immediate. Versus would you want to wait for a year in the hope of getting a better transplant? You're not going to want to wait because there's serious sort of quality of life and other issues associated with being on the wait list, being on dialysis, and so on. And so what we want to do is we want to actually consider the other extreme, which is let's suppose we have arriving pairs that are compatible, but they're only willing to enter into an exchange if they can immediately get a kidney from the exchange, right? So this is kind of a pessimistic assumption. Maybe we could have them wait for a little bit longer, but it'll give us a bound on sort of how much we can improve the system. So we built a model to specifically evaluate this, and just to walk you through what that model looks like, right? What we're going to see is we're going to see a pool, that's the red agents, so what we call standby agents, who are the incompatible pairs. And they have some compatibility within, we have some compatibility that we have figured out within those. But that's not a constraint that we have to proceed immediately, because those people are already on a wait list. They can't proceed with their own donor. That would have to be mediated through the exchange. So we have this incompatible pool that's waiting, and then we have compatible pairs that arrive one at a time. When a compatible pair arrives, what I can see is, what is the quality of different possible matchings that I could make? So for example, this blue pair arrives. The quality of the internal match there is 5. The quality of this match with the red agent over here is 10. So I could potentially take that, but let's say my algorithm tells me, don't take that match right now. Then that pair matches internally. It goes away. A new pair arrives at the next point in time. This one is not compatible with any incompatible pairs. It's only compatible with itself. So that match proceeds. Time goes on like this. Another pair arrives. In this case, we're actually going to proceed and do this match. So then that red pair disappears from the incompatible pool. Another pair arrives. Let's do that match as well. Then let's say time comes to an end, or like our batching mechanism ends at that point in time. The world ends. Nothing ever happens again. And then we have this situation where we're going to proceed by just matching those who are left in the incompatible pool at that point in time, right? So that's the model that we're going to work within. So this is a complex problem to think about, and it's really where sort of the algorithmic innovation has to happen in order to figure out sort of how do we actually proceed with matching over here, because you're greedy algorithms in general are not going to be the best algorithms for these kinds of problems. So what we do is we consider a relaxed integer programming formulation of this problem. I'm not going to go into sort of too much detail about it, but basically we write this down as an integer program where we have weights that are associated with match quality, and then we have variables that we're going to solve for, which are going to tell us, do I proceed with this matching or do I not proceed with this matching? And then I put in constraints, and my constraints tell me about the system. So this constraint, for example, says each online agent matches either with itself or with one of the agents in the incompatible pool. Similarly, each standby agent matches with exactly one other agent, and so on and so forth. And then we proceed with kind of a standard set of tools in this optimization literature that says, all right, if you have an integer program, one way that you can go about sort of getting an approximate solution for that, because this is a canonically NP-hard problem, is to then relax it to a linear program, solve the linear program, and then figure out what to do from there. The cool thing is that we can actually write down what's called the dual of the linear program, and that's going to give us an online algorithm, because solving the integer program is a complex thing to do. If we actually take the dual, one very interesting thing pops out of that. So this is stuff that, like, you can do, and that there are ways of doing it. So there's a whole literature on primal dual algorithms. The really cool thing about it is that every constraint in the original formulation corresponds to a variable in the dual formulation. And it turns out that this dual formulation that we can get from the original problem has a very nice interpretation where you get a value, either alpha or beta, that you can actually think of as the estimated value to keeping a pair in the pool rather than matching it right now. And that gives you a really nice online allocation rule that basically says, hey, if you should only be willing to take a really high value pair out of the pool if the value that you're getting from matching them right now is very, very high. So you actually optimize over the difference between the value that you would get, which is WTI down here, and this beta I star value, which is what we've computed from the dual, which tells us, hey, this pair has great value. And what you would expect to see is that, if I go back to like that picture that I showed you, right, this pair over here, for example, is connected to two different pairs. And so it's going to have higher value because there's multiple different things that I could do with it if I don't match it to somebody right now. So that's the kind of intuition that you would get from that. So, all right, so we go through the mechanics of this. We use this as sort of our basic algorithm for solving the problem. There's one sort of step left over here, which is that we don't actually want to go through and compute these beta values every time. So we're instead going to use a machine learning approach where we basically simulate out the process many times in advance. And then we solve the dual to get these beta values, which is an expensive operation, but I can do it all beforehand. And once I solve that, I'm going to try to then learn a model that goes from the demographic and medical information I have about a pair to a predicted beta value. In this case, it turns out that I can just use a linear model. It does pretty well. We don't see many benefits from going to more complex models in this case. And this kind of shows you, how good the prediction is. So we've got the prediction on the y-axis over here and the true beta over here. And you can see that, like, I do a pretty good job overall of doing this kind of prediction. So finally, I want to take this algorithm and I want to evaluate it in terms of, like, what would it actually mean if I were able to use this algorithm. So, so there's two different things that I want to think about when I evaluate it. One is, when I actually use this, what is the increase in the number of incompatible pairs that I'm able to match? Because that's sort of one big goal that I'm striving for over here. And then the second question is, what is the increase in the expected survival time for the compatible pairs? Because that's the other objective over here, is to give them better outcomes. And this is kind of, our main result over here. This kind of shows what would happen if you were to use these algorithms. So ODAS is the algorithm that I just told you about. OAES is a more expensive one where I'm actually solving this integer program at every point in time. The oracle is how well I could possibly do if I had information about all future arrivals at any point in time, which obviously I'm never going to have, but it gives me an upper bound on performance. All right, so the baseline, that is when I don't include compatible pairs, is that I will get about 55% of my incompatible pairs matched. All right. If I include compatible pairs in the model, that proportion jumps up to like between 70 and 75%. So I'm getting a 50% increase in the proportion of incompatible pairs I can match by including compatible pairs. And remember, for each of those compatible pairs that matches with an incompatible pair, they're getting a better kidney in expectation. So this is kind of a win-win over here. How much better? Well, we're seeing that on average, the expected graft survival of compatible pairs is going up from 9.6 years to something like 11.1, 11.2 years in the simulation. So that's a year and a half. That's a pretty substantial win, right? That's a year and a half less of having a kidney that is failing, like being about to go on the wait list, potentially being on dialysis, and so on and so forth. So these are significant benefits that we're estimating we could get if we were able to do this. And so we're now thinking about how do we actually transition this to actually implement it and go from there. There's some interesting sort of algorithmic questions as well that we can think about, but the other sort of headline result that I wanted to show you is that people sometimes worry in kidney transplantation, in living donor kidney transplantation, about effects on different subpopulations. And so, for example, one famous problem that we're often worried about is that recipients of type O are much harder to match in general. And actually, recipients of type O are dramatically overrepresented in the African American population. And so this has been sort of a systemic problem when people have been thinking about this. And so if you see, pairs with recipients with type O blood are getting matched at a 32% rate in the original without compatible pairs. But with compatible pairs, they get matched 62% of the time. So doubling that, which proportionally is more than the overall impact. So we're actually doing relatively more for that population than for the general population. So that's good news on that front. So I'm going to skip specific comparisons of the algorithm. But the main thing that I want to say over here is that when we use these kinds of models, right, predicting outcomes, in this case by modeling the quality of the match explicitly, allows us to then incorporate these compatible pairs and introduce a richer mechanism into kidney exchange than is currently used. And in order to do that, right, we had to think about a number of different things. We had to think about how do you model match quality, how do you do this prediction. We had to think about the incentives of the agents. We need to do dynamic matching. We want them to get better kidneys than they would otherwise, and so on. And then that gives us all kinds of potentially pretty cool results and the potential to really end up hopefully influencing practice in the near future on this front. We're actually, I'm hoping that we'll soon be able to sort of, talk to the surgical team about working with them to actually monitor the real flow to see, okay, we're doing a lot of modeling over here. There's many a slip between the cup and the lip. What happens in the actual, they have a weekly meeting where they decide, what's going to happen, where they track each pair. We're hoping to actually follow this over time to see, how long does it take to actually go from your first appointment to getting transplanted if you happen to be a compatible pair. So how much time do we have to work with? What are the situations where things fall through or people don't follow up and all of that kind of stuff. So we're really interested in doing that. And then we'd like to see if we can take this into practice and see what happens if we start offering people the option of participating in exchange, even if they happen to be compatible with each other. So we're excited about the possibilities on that front. What I want to do very briefly is talk about our other work, which is actually, it seems like a very different domain, but it ends up having a very similar flavor to it at the end of the day, which is work on, and this is also sort of modeling work, but based on real data, on homelessness. And so homelessness is a huge problem. We have more than 1.5 million people often homeless in any given year in the US, and we just do not have enough resources to meet demand. there's been somewhat limited assessment of how effective the different mechanisms for allocating resources to homeless populations are. For various reasons. I mean, it's tough data to work with. It's not very clean at all, and like you need to think about things pretty carefully. But what we wanted to do was we wanted to look at a specific data set that has data on folks who are calling a hotline, and then they're getting assigned to one of, so these are people who are entering the homeless system for the first time, and they're getting assigned to one of 4 different types of interventions. These are transitional housing, which is a fairly intense intervention that involves counseling services along with a place to live. Rapid rehousing, which gives you very quickly a new place to live, but not so much in terms of counseling resources and so on. Emergency shelters, which are the canonical view of like, you go into a shelter, you're hoping not to be there for very long, but it provides a stopgap, at least gives you a roof over your head. And homelessness prevention, which is intended to give small allocations of resources and sort of networks of referrals to people who are at imminent risk of becoming homeless. So an example would be a cash transfer, or perhaps a way to settle a utility bill that would otherwise lead to your heat getting cut off and not being able to stay in your home, that kind of thing. So our idea over here is to see if personalized intervention would lead to better outcomes in the system as a whole. And we're going to measure this by saying, okay, once somebody enters the homeless system and they exit, do they re-enter the system within the next 2 years or not? That's our sort of measure of interest. So what we're going to need to do is we're going to need to measure the counterfactual, which says, okay, suppose this household had been allocated to a different intervention, what would their probability of re-entry be in that case? All right. So we have detailed demographic and assessment data from a number of different homeless agencies. And we use an ensemble method called BART, which is Bayesian additive regression trees, which are really sort of good with counterfactual probabilities to estimate these re-entries under alternative sort of realities, right, where one household gets allocated to something different. And then what we're going to do is we're going to say, okay, let's take these predictions and let's re-optimize based on these predictions and see if we would expect to see better outcomes when we do this re-optimization. So just to give you a sense, this is the data that we have over the course of about 6 years. We have very different base rates of re-entry, right? 56% in emergency shelter will re-enter, only 24% in homelessness prevention, but these are very different populations. So you can't just do an apples-to-apples comparison, you have to be more careful than that. The data that we have is actually very detailed. It tells us a lot of stuff about these households, including things like, is the head of household a veteran? Do they have a disability? Do they have substance abuse problems? What kinds of substance abuse problems? What is their monthly income? We also have data from that we have features that we construct. So how often have they called the hotline? How long did they have to wait to get into the system? And so on and so forth. And now you'll see sort of this optimization trick coming back in, which is we formulate this again as an integer program that says, okay, suppose once I have these probabilities, Pij is the probability that household I would re-enter the system if allocated to intervention J. What I want to do is I want to come up with a matching that will tell me, okay, I should allocate household I to intervention J. And I can only allocate each household to exactly one of the interventions, and each household must be allocated to at least one intervention. And we have these 4 different interventions that I talked about. So the interesting result over here is that according to our estimates, we would reduce the number of re-entries from 43% down to about 32% with the optimized sort of reallocation over here. So there is potential to do better than is being done in the current system. And we're fairly confident that at least as much as these things go, this is a reasonable estimate because you could ask, okay, do these counterfactual probabilities make any sense? But we can actually measure the estimated probabilities of re-entry out of sample, the way you would traditionally do in machine learning, on the actual interventions they got allocated to, and then see what would that predict. And you can see that that prediction is 2,227, which is pretty close to the 2,193. So we could be hopeful that that this reduction is something that is relatively realistic, although times have changed so much that like you can't really think that you would go out there and do this right now and you would get the same results. But it's a question of like, historically, could you have done better? However, when you look at this, there's a fair number of households that are getting hurt and a fair number of households that are getting helped. So the ones on the right are getting helped over here. They have a lower probability of reentry than they did earlier, but the ones on the left are getting hurt. So what can we say about that? So what we did was we trained a machine learning model to try and predict, will a household be helped or hurt by the new allocation, right? And we looked at only households whose allocations changed. And then we tried to look at sort of which features were most important in deciding whether a household would be helped or hurt. And actually, interestingly, we found that the new allocation potentially seems to help families that are worse off in some ways. So it tends to help those who have lower monthly incomes, that have had longer waits to enter the system and made more calls to the hotline, and typically ones that have more substance abuse problems that they're dealing with. So actually, this sort of machine learning method over here, or the AI method for reallocation, seems to potentially be helping out the more needy families more in this kind of a situation. Finally, you can do a version of this where you instead look at a constrained version that says, okay, you can't hurt anybody too much, and then when you add constraints like that, you're going to get sort of less overall benefits, but you can give a guarantee that, like, at least in the new allocation, nobody's getting hurt more than a certain amount. So you can set that threshold how you want. We set it to 5%, no more than a 5% change in the probability of reentry under the new allocation compared with the old allocation. So overall, I just want to talk about wrapping up to some extent, which is to say, all right, we're interested in thinking about allocation of these scarce resources and also moving from a model that's really focused on efficiency and overall social utility to a model that would look at different notions of social justice, and how do we incorporate that into our models to try to figure out how should we be doing these kinds of allocations. And so we're looking at thinking about sort of notions of justice from the philosophy literature and intersecting with political philosophy in that area. We also have this very interesting sort of technical problems when you think about, all right, I'm talking about these 4 interventions, but actually the whole landscape is more complex than that. I could potentially be allocating different bundles of resources to each household or family. Could I do this kind of combinatorial allocation and get better results than I do using just this straight up, I have to choose one out of 4 different resources here? So overall, I think we're very interested in this area of how can we use data, how can we use AI in the service of efficiency, equity, and justice. I think that there's an incredibly interesting interplay between doing optimization of the kind that I've talked about over here and the outputs of prediction models that are coming from machine learning, and that sort of this intersection is where a lot of the technically interesting questions are. How can we do better prediction in the service of optimization, and optimization that effectively integrates prediction? And ethical and systemic issues should really be primary as we keep thinking about these kinds of problems. So thank you for your time. I just wanted to put up a picture of all of the people who have participated in this work, and thanks for funding from the WashU Institute for Public Health and various NSF awards. And so thanks for your attention, and I think we have a few minutes for questions, hopefully.
All right, so we got time for 1 or 2 quick questions.
I'm very interested in these kind of problems, solving them in a enterprise situation. Can you talk a little bit about the technology you used? It seems like you're using a lot of graph terminology. Are there graph tools that you like? And then the integer programming stack as well.
Yeah, sure. So a lot of the integer programming stuff, I mean, we've used different things. So these days, we're using a lot more like Gurobi, basically, and interfacing with Python on the integer programming kinds of stuff. We just write a lot of our own code for most of these things, and so most of it is stuff that we've done. And most of it these days we do in Python. So we use Python. We interface with scikit-learn, with Gurobi for our typical kinds of applications over there. BART is another sort of useful part of the package. And so the stuff that we're doing with BART has actually mostly been done in R. And we've been using sort of R and BART for analyzing that data set, basically.
What about graph tools?
So I mean, most of the graph stuff that we're doing, right, is you don't really need to get like very deeply into anything particular on the network. So so we think a lot about these problems, but at the end of the day, what we're doing for the most part is we're formulating a graph problem in the language of LPs and IPs, and therefore we don't actually need to explicitly represent the graph beyond the programming formulations. So,
Thanks.
Yeah, sure.
It's kind of at the edge of your scope, at the end of it. But it seems like you pretty comprehensively demonstrate that a better allocation of resources could produce more benefit for more people with no greater total resources. Do you think that will be effective in helping persuade the political and social decision makers that cause there to be 59 different organizations serving the homeless in your sample metro area, that they should consider merging themselves together instead of there being 59 separate?
So that's a really, really good question, and it's a very hard question. So there's various issues that come up on that front, right? So homelessness policy, I'm not an expert in this, so my colleague Patrick Fowler is really the expert on that front. But here's my understanding of what's currently going on that front is that there's a lot of places. So one thing that's sort of, I think very important in social services is you don't want to dissuade someone from doing something that they think is good, right? So these 58 different organizations that I'm talking about over here are typically places that are running shelters and like doing stuff like that. So they have their own intake. So it used to be the case that there was a centralized hotline. And the hotline actually had information from all of these places. And that's where our data is largely from, is from the hotline. So my answer to you is unfortunately going to be negative in this front. So the hotline existed, and they had the data, and so they could figure out, hey, there's vacancies over here. This would be a good place to send this person who's calling and in need. Resources for the hotline have been going down. And so there's effectively, at least my understanding of it is that, like, people are doing more and more sort of decentralized intake at this point, which is not necessarily good for our data collection systems. The other thing is that there's been a big push, there's been a big push towards providing more permanent supportive housing, which is something I didn't talk about over here because that's really for the most vulnerable populations. And this is sort of the edge of what we're thinking about these days as well. So, so don't take this as, this is just our current thinking on some of these issues. So what happens is that permanent supportive housing is a very visible but very expensive thing to spend a lot of resources on. Effectively, I think resources are being taken away from other programs like prevention in order to have more permanent supportive housing. Now, it's really a question of, it's a normative and political philosophy question of whether you want to spend more resources prioritizing the most vulnerable, but I think there's dynamic issues over there as well, which basically say, hey, if you prioritize the most vulnerable today, will you be creating more vulnerable over time because you're not supporting people at the point where perhaps giving them support would prevent them becoming super vulnerable? I don't have the answer to that question, but I think it's a question that we need to be engaging and thinking about pretty deeply. It could be controversial, but it's something that we really should think about. And I think this thing between centralization and decentralization is very complicated because you really want to be allowing people to do things that they think are going to be helpful to the population. But at the same time, there are definitely sort of, benefits to the system as a whole from being able to say, hey, there are spots over here if you call the hotline, or if you, maybe if one could design an app that people could go on, because it turns out that, like, there's all kinds of research that shows that, for example, becoming homeless, you still typically have access to the internet and Facebook and things like that for a while, right? And so if there are apps and things that can connect people anonymously, perhaps, to resources that are open and available to them, perhaps that could be useful. These are all sort of things that I think are interesting questions to be thinking about and super important. And I'm sorry I don't have like a great answer or strong opinion at this point, but it's stuff that we are investigating. So.
All right, well, unfortunately, that's all the time we have. Another round of applause.
Thank you.
Thank you so much.
Thank you.